Hi all, very nice to see you all coming here to this quite informal show of our test facility that we have here at Värtan. So I'm Fabian Levihn, so I'm head of R&D here at Stockholm Exergi, and I'm also a part-time researcher at the Royal Institute of Technology in Stockholm at the division of or the Institution of Industrial Economics and Management. So I share my time in between those two places. And today I thought I should show this test facility that we have for BECCS. With me today, which I will try to show you, I also have my colleague over here, Jonas, that will help me with taking some questions from the chat and also help me with everything around it. So he's the one that's on my other Zoom account, so to say. I think it's really nice to see so many showing up, and because it was an open Zoom link, we will have we will keep everyone muted. For now, anyway, we might change that later, but we don't have any control over who's logging in or not, so we don't get any trolls. So that's the reason why you are muted. But if you like to post any questions, you can just take them in the chat, and then Jonas will catch these questions, and we will try to answer them as well as we can. I thought that I would also just start by giving sort of a short background to the whole notion of bioenergy CCS and why we're talking about it. And Jonas, do you want to take the next picture? So this is done in Paint. At least the name of it was Paint once upon a time. And this thing is basically the big basic of BECCS. And of course, it's quite fundamental, but in some regions, it's a little bit more discussed than maybe what it is in Sweden. But if we take fossil fuels, what we do is that we take carbon from the bedrock and then we add it to the atmosphere, while biomass, if properly used, and if you have a sustainable forestry and you replant trees after you take them down and use them, or trees replant themselves after they are fallen and are left to rot in the forest, then what we will have a circulation of CO2 from the atmosphere to the biomass and then back to the atmosphere. So that's the basic. So then if we take the next slide, Jonas. So when we talk about climate change abatement, we have two options. So we can reduce the fossil emissions. So that's basically just, we could switch to other products. That's one way. We could stop using fossil fuels. Or as in the term of carbon capture and storage, what we could do is that we take the emissions from the fossil fuels and put it back in the bedrock. That's one way. For those emissions that for various reasons we can't reduce, we can counter them instead. And that's why we talk about bioenergy CCS. And through photosynthesis, as trees bind carbon from the atmosphere as they grow, that gives a cycle of carbon atoms basically from the atmosphere to biomass that basically collects all the carbon, and then we can store it in the bedrock. So in climate change abatement, we have two options. We could either reduce emissions or we could counter them with these so-called negative emissions. And biomass CCS is one of these technologies that provides a flow from the atmosphere into the bedrock. And instead of a tree, we could put like a factory instead, and then we would have what is called direct air capture that basically use membranes or something else to catch CO2 directly from there. But the whole thing that biomass does is that it concentrates all of these CO2 that's in the atmosphere into the cellulose, and then it's possible to use it. So next slide. So when talking about climate change abatement, and sorry for some of the headlines being in Swedish, so this is a little bit Swinglish, this short presentation, before I will also show this test facility that we have. But the background for BECCS is that almost all pathways that provides solutions to meet the Paris Agreement, they require these negative emissions. So there are emissions that we can't reduce because there's a lack of technologies, or it's a lack of economically feasible options to reuse it. And in Sweden, a governmental inquiry has, for example, seen that you have these diffuse emissions from the agriculture sector. For example, as you plow agricultural land, then you have a release of nitrous oxide, for example, you could have. And that's very hard to get to. So if you want to still, all of these things that you can't reduce for various reasons, like these, like in the agriculture sector, then you might want to counter it with these measures that's called negative emissions. So globally, we're talking about quite a lot in all these scenarios that IPCC works with. So they have these big models that they run and trying to find solutions how to reach the Paris Agreement. And we can really see that most of these models, they rely on bioenergy, carbon capture and storage. So taking CO2 from the atmosphere into biomass and then put it in the bedrock to counter emissions that we can't get to. Also in the EU long-term strategy, the target for 2050, that one will require somewhere in between 281 to 606 kilotons of CO2 per year to be removed with these negative emission technologies. It doesn't have to be BECCS, it could also be direct air capture or biochar or other technologies, but we still require quite a lot of carbon removal from the atmosphere. And in the Swedish context, we know that even to reach the Swedish national targets, then we need up to 10 megatons of negative emissions by 2045. And we also know that there are great regional differences in the potential to apply different of these carbon dioxide removal technologies. What we also see is that if we have more stringent climate change abatement targets, if we aim to keep the temperature well below 2 degrees and closer to 1.5 degrees, then we need more BECCS than if we allow the temperature in the atmosphere to become warmer. So that's the sort of basic. What we at Stockholm Exergi, we thought that, of course, because we see that there are other sectors that demand this and that this is something that we could do, this could add an additional benefit to the use of biomass. So besides producing, as in our case, we make district heating and electric power, we could also add the service of removing CO2 from the atmosphere to counter emissions in other sectors. And of course, you could also do this, for example, in the pulp and paper industry. But then you need to have, and that's, I think, is a very, very important background, that you have a sustainable forestry in the background, where you replant trees and you have this real cycle where trees are allowed to regrow and everything. Sorry about the noise in the background. So we are at this industrial site, of course. So next slide, please. So this technology that we're looking at, we always get also this question if is it hard to catch CO2? And these technologies, they have been available since the 1950s or even earlier. The particular technology that I will show you where we have a test facility, it was used in the gasworks in Stockholm from 1971 to 2011. And it used something called hot potassium carbonate. So it's potassium carbonate that you pressurize the flue gas in a first column, and then and I will talk more about this later on as I show the test facility, because I think it will be a little bit easier. But basically it's a column where you have potassium carbonate that reacts with the CO2 in the flue gases, and it's about 18% CO2, biogenic CO2 in the flue gases from a combined heat and power plant, or our combined heat and power plant. So we compress this, we have a reaction between potassium carbonate and the CO2 in the flue gases. This is in turn taken into something called a desorber, where the pressure is released and some heat is added, and then the bicarbonate that you then have will release the CO2 as the temperature goes up and the pressure is reduced. So bicarbonate, many of you baking bread are familiar with. So bicarbonate, it works exactly in the same way as this capture process. So what makes bread fluffy is that CO2 from the bicarbonate is released in the baking oven as you get about 100 degrees Celsius. And this forms small pockets or small bubbles in the bread of CO2, and that's basically what baking soda works like. So that's a bicarbonate. And potassium bicarbonate is used as an industrial baking soda, actually. So it's quite an easy process, I would say. So with this whole background, I think we could quit the presentation there. I think for us, the big thing with this whole carbon capture, it was in 2016, and after the fifth assessment report from IPCC, we could see, as I told you before, a lot of scenarios, and in particular it was 101, 116 scenario reaching the Paris Agreement relied on BECCS, and we started thinking about it. Okay, so what's our role in this? In spring 2019, in the spring budget, the government added some money so that you could provide these test and research facilities and demonstration facilities for testing this carbon capture technology. So what we did is that we supplied an application to the Swedish Energy Agency, which was approved in August, and then in about 4.5 months, we could build a test facility to actually test this technology. And I'm standing in it right now, which I think is really cool. And it looks like, if I are able to turn my camera around. It's always interesting when you do this on the mobile. So the test facility looks like this. You can see Jonas sitting in one of the corners right there. And I'm just going to change this screen. And this facility, it looks like this. And what you have here is basically the same thing as we had in the gasworks here in Stockholm previously, that was operated for a very long time. So we take the flue gases in, and it goes into this regular Atlas Copco compressor and compress the flue gases to around 7 bars, 6-7 bars. Then it's taken into this absorber that's here, and then you have this where the flue gases are coming from below, and it's mostly nitrous gas, which is sort of the normal compound of air, and then you have 18% of carbon dioxide, and the carbon dioxide is then goes up into this absorber like this, the flue gases with carbon dioxide and nitrous gas, and then the potassium carbonates flows from above like this, and they meet with each other. Then you have a reaction of this in this. Here is the actual absorber and the compressor. So the flue gas comes into this compressor, and then it goes into this absorber. And in this absorber, that's just a pressure vessel where you have this kind of packing material. So this is nothing magic. It actually costs quite a lot, but it's nothing strange. Or it depends on what you're comparing it with. So it's just big cylinders filled with this packing material. So about 1 meter of these packing materials inside this cylinder. And this is just to provide a big area as the potassium carbonate is flowing from above and into this absorber. So you want to have as much surface area as the potassium carbonate, and it's a potassium carbonate about 30% mixed with water, flows through this absorber. And then the flue gases goes up, and then because it's pressurized, you have this reaction where the potassium carbonates forms bicarbonate. So basically what you're doing is that you're creating baking soda. Then you pump all this potassium carbonate to here above, and then you just let it stream down, and then you have this second column, which is this vessel, which is filled with that packing material. And then you release the pressure to atmospheric pressure, and then increase the temperature to 105 degrees. And then what happens is the same as in the baking oven, that the baking soda or the bicarbonate releases the CO2, and you have a clean stream of carbon dioxide that you then can transport and compress and take away. So yes, I think it's really cool. This particular facility, it's also something that we're quite proud of. So with help of consultants, we could, as I told you before, we could make this with the help of consultants and this mechanical firm in Norrköping called Guidningen. We could make this and produce this facility. And when it was going to be marked, this CE marking, they were asking, okay, so but who's the supplier of this? And this is our technology. So we haven't brought any technology, any sort of ready technology. But this whole facility is created from off-the-shelf equipment. So the packing material, these things that the cylinders are filled with, that's a normal Sulzer packing material. We have a normal Atlas Copco air compressor that works perfectly well with flue gases. And these columns are sort of regular pressure vessels that I think was, we were allowed to have up to 20 bars or something, but normally we operate them at 7 bars instead. And this one is at atmospheric pressure. What also is really cool, I believe, is what we've done with this is that we shifted the whole mindset of looking at carbon capture. So traditionally, when they looked at carbon capture, the whole aim has been at finding the solutions for capturing CO2 that has the least energy penalty. So that the whole focus has been at developing technologies and looking at technologies that use as little energy to catch the CO2 as possible. And that's because you have looked at condensing units. So if you look abroad, outside the Nordics mainly, then all of these big power stations, they cool away all heat and then they only produce electric power. So they're looking at processes where all this heat that they cool away can be used to catch CO2. What we have done instead, and our focus and what is quite unique, and then now I know that other actors in Sweden have also begun to think about CCS in a similar manner, or INBEX in a similar manner, and that is how to catch and recover heat from the process instead. So instead of having the sole focus at finding ways to reduce the sort of steam or electricity used, we're looking at how can we find a process where we can recapture and recover as much heat as possible from the process. So of course it takes electric power, having a compressor like this run, and if we're looking at full scale, so putting this as the big CHP in Sweden, that would create about 800 tons of negative emissions per year. Something like 800,000 tons of negative emissions per year. What we also would have then is, at the same time as we would create some 100 megawatt of electric power as we run this facility, but we still lose somewhere around 20-30 megawatt. So we lose a lot of electric power, but because we have this absorber, the baking oven, that one operates at 105 degrees, which is a very good temperature to recover heat into district heating. That means that all energy used from the compressor to the absorber and desorber, that can be recaptured in the process. And what we see is that this energy penalty that we talk about, that for a condensing unit is somewhere in the range of maybe some 10, 15, or even 30%, you lose that of the electric power. Here we take electric power, but we can get it back as district heating. So the overall total efficiency is only dropped 2 to 3%. That is what's really unique for us and what makes this process really interesting. And I know that some of the big players abroad have actually started to think about turning condensing units into either industrial combined heat or power, or even thinking about district heating in relation to carbon capture, because there are fundamental benefits of looking at carbon capture in relation to where you can actually recapture the heat, either for other industries that you could form an industrial cluster, or because you have district heating. And I also know that there are some industrial plants that right now are looking into if they also, by optimizing the temperature levels for recovering heat, and they can recover heat that's usable for the process, even though they use some primary energy. So while, but of course, that we lose some electric power, that's still a problem, that we use this compressor. But another good thing with this process is that it's quite flexible. So during these hours when electric power is demanded the most, then we can sort of bypass the carbon capture and operate the combined heat and power plant as this regular climate change neutral, where you only have biogenic CO2, combined heat and power plant fuel, and we only use residues from forestry basically. So secondary biomass, run it in as a regular combined heat and power plant during these hours, and in Stockholm that's somewhere in between 0 to some 400 hours per year when you have this grid congestion, and for other reasons you have a very high demand for electric power. The other hours you can have full capture and catch as much CO2, and then you would have an annual capture rate of somewhere around 90%. So that's perfectly feasible to do. But then that's also an optimization for the circumstances that we have here in Stockholm, where we have grid congestion, we have a lot of wind power and so on. But there aren't that many hours where the power situation really is critical. But these hours we can supply full electric power, 135 megawatt. And then when there is an abundance, especially of renewables, then turning a little bit of steam that otherwise would be used for electric power, or using an electric compressor, it's not that big difference economic wise. Of course it costs money, but it's still cheaper comparing to looking at these regular condensing units. And I think I will actually stop there and see if there are any questions.
Well, we have gotten quite a few, Fabian. I think the first question we got was, read that from Mikael, I'll read it out for you.
Yes.
I kind of understand that this is one of the central questions, but who would be paying for the service of removing CO2 from the atmosphere? What's your view on that question? Is it taxpayers? Could other fossil CO2 emitters be possible to collaborate with so that they don't have to pay for emission allowances? What kind of emitters in that case?
I think the answer is yes, because I think you put your finger on sort of the possibilities. Actually, we don't know yet. So we worked with this because we saw a growing demand for this for having negative emissions. So that's sort of our background into this. But what we see, so there was a governmental inquiry called, and now excuse my Swedish, Klimatpolitiska vägvalsutredningen, that left a big report that you can find. It's SOU 2020:4, which basically I think Jonas can write in the chat. And this showed that even if you reduce all the emissions that you have in all sectors where it's feasible, you put CCS on all industrial processes that have fossil emissions and so on, then you still would have all of these diffuse emissions and the emissions that you can't get to. And it would mainly be in the agriculture and some other sectors and some others where it's really hard to catch the emissions. And this inquiry from the government, their conclusion was that it wasn't feasible to put cost on agriculture to provide countering these emissions from plowing land, for example, and that for that reason they suggest that the government should pay for it to sort of aid in countering the emissions from agriculture. But as a bridging solution, until we have all of these other emissions reduced, we can see that there are some sectors that, for example, in the near term lack technologies for reducing their emissions, and then you could counter their emissions. But here I think we also should be clear about that, and I think IPCC is also quite clear about that, negative emissions technologies, to be compliant with the Paris Agreement and all the trajectories where we reach the Paris Agreement, we really must reduce these sectors. So it can't be a sort of a bailout for just keep ongoing business as usual for all the fossil sectors. but it could be a bridging solutions until they have technologies in place. That's how it could be used. And then we have maybe the third, and here you could find bilateral contracts in the market for this. And then we have the sort of third case. So the first one, that would be the government requiring a certain amount to reach the sort of what Sweden has committed to under the Paris Agreement. Could be other nations that look into buying it as well. The second category, that's bilateral contracts then. So that's a possibility. We see an increasing interest from corporations that's interested in buying negative emissions. And then we have this sort of, the third case is more like these that want to do things for good sake. For example, Microsoft have proclaimed that they want to counter all emissions that Microsoft has contributed to since they were founded in the 1970s. So then that's a possibility as well, doing that for that reason. So there are people that want to do it for various reasons, and they also have a very, very large budget. And we see more and more corporations where there are also an interest for doing things like that. So I would say that any of these three would be possible.
Cool. An entirely different question. What is the life of this absorber material that you've shown? For in how many months does it have to be changed, if you know that?
Yes, actually I do. So from the gasworks where we had the same process, we know that the technical lifespan of things like this is about 40 years. So in the gasworks, now I didn't bring a picture of its internal with me out here, but what we could see is that after 40 years of operation, it still looks not like new, but it doesn't look that used. I actually have this potassium carbonates that's inside these columns, and we see that about 10% of this potassium carbonate needs to be replaced each year. So that's the sort of same amount that we also saw at the frequency. So the pace of replacing potassium carbonate is about the same. So about 10% of this per year. And potassium carbonate, what it does, it forms a salt. And I think they actually have, so it forms a salt like this. You can actually see here. So here's a salt that's formed by the potassium carbonate. So it's basically this baking soda thing. So you need to empty it and replace a little bit of this. And you could also have some of the smaller things in the process that actually would sort of get some of these traces of well, you have particulates in the flue gases and some other things that are really low in our case, but still could form salts with potassium carbonate. So about 10% per year needs to be replaced.
Cool. Another question: if anyone, if you asked a question and Fabian sort of missed the point or you didn't understand the reply, don't hesitate asking again. Otherwise, we'll jump to the next one. Maybe I'm jumping ahead. Jacob is writing, but is there a potential use for the captured gas other than pumping it into the ground? And also, are the geological requirements for pumping into the ground strict? And what's the life cycle analysis of the CO2 system?
Yes, so we actually did a life cycle analysis of this system. You can find it in at Science Direct in Biomass and Bioenergy. If you just Google my or search for my name there as an author, you will find that one. So then you can read it. So that's about my best suggestion. So all in all, it's sort of, we're talking about the percentage of the amount captured. So that's the sort of leakage or rebound, or maybe not rebound, but the sort of leakage due to you have for various reasons, because you don't have these ships utilizing renewable energy. In best case, they're utilizing natural gas instead of heavy fuel oil, at least. But still, a lot of ships are driven by fossil fuels, but it's and then you have some other parts in the process. So from a life cycle assessment, you will still have some. It's still about the individual percent. When talking about this storage, some people they sort of think that it's a big cave that we're going to store CO2. No, it's a porous bedrock and we are part of this big Northern Lights project where we're sort of and that's the ones we're discussing storage with the most. And they're looking at in this porous bedrock that's a big aquifer where you store the CO2 at 3,000 meter depth. At 3,000 meter depth, you have 300 bars of pressure. So the actual pressure helps in part. So because it's an aquifer, what you have is that what you create is in part soda stream in the water down there at 3,000 meters. And it's then I think the depth in the water is about 1,000 meters. So it's 1,000 meters of water, and then it's 2,000 meters of different rocks. Where at the bottom it's this porous rock filled with water. So one thing capturing is just solving CO2 in the water like a soda stream. The other one is that you have, because it's not a big open cavern, it's a big, very small, these porous formations. Then you will have some physical trapping of the CO2 bubbles just because of that. Then you have this hard bedrock above the porous material, and that also provides a cap. And then over long term, what you actually have is a mineralization of the CO2 at that depth. So it's four different things that keep the CO2 down there. And Norway, they have been storing CO2 since 1995 in one project, and have one additional project going now. So from that perspective, that they can see that storage, I would say, is there's quite a lot known about it, and it's not that hard, but you need to store it in the right place. And it's not depleted gas fields. It's not about getting more oil up in our case. It's about having dedicated storage in this saline aquifer, it's called. So it's this porous bedrock with water, basically.
And is there any potential use?
Sorry, that was the question as well. Yes, yes, of course. Yes, there are. You could use it. So some are looking at combining biogenic CO2 with hydrogen to form methanol, which could be used as a sort of electrofuel that's sort of usable in more conventional engines. So you could do that. Then you could replace fossil fuels, but what you couldn't, of course, then you would have a release of the CO2 back to the atmosphere. So that would be a renewable fuel and not a negative emission, which is another thing. Then there are research on how to put this into building blocks, like creating polymers or something by combining this CO2 and having that stable, and then you could create buildings out of it. My own reflection is that is probably a couple of tens of years away, and we also don't know how stable they are yet. So there are some you could maybe combine it with iron sponge and other things. But the question also is, how long will it be stored? So will that one be stable for 100 years, or are we looking at the same as geological storage, where we're talking about permanently storing it, basically?
Awesome. We are getting so many questions. It's awesome.
Yeah.
Engagement. Another one is Dilip is wondering if you could elaborate on comparing with other bio-CCS technologies or plants in terms of costs and energy required to run the plant. I think he means the facility rather than the plant, since the plant produces electricity.
Yeah. Yes. So I think this is, I think, the big thing where we lose electric power. So this is a test facility. We wanted to evaluate degradation and some parameters, and there also is a lack of data. So there still is no fundamental data. So we need to continue and expanding this into, we would require to expand this into a research facility to fully understand everything. So what this test facility has told us is that, yes, we can run this technology, we can catch CO2, we won't get any unforeseen degradation. But if you want to do this in a sort of an optimal way, there are a lot of sort of gaps in knowledge that you only can sort of get through by trial and error, because these chemical reactions that you have could be, they're extremely complex. So if you don't have any reference point, you don't know exactly what will happen. So there's still a lot of research actually required to do this. So we know that we can do it, but if we want to do this optimal and reduce the energy as much as possible, more research is needed. If we talk full scale, so this compressor, instead of being like this, then it's a big house, and the absorber is actually 7 meters wide and 65 meters high, instead of now being the inside is about 1.5 decimeter, and then it's some 2 meters high with 1 meter of reactive surface. So then it's a lot larger. So then we're talking about having maybe losing 30, some 20, well, in the range of 20 to 40 megawatt of electric power. So the power output normally is 135 megawatt of electric power. And then basically all of that. But that also includes liquefaction. So basically compressing and cooling the CO2 so that you can transport it away. So that is also included in this number. So 20 to 40 megawatts of electric power from 135, somewhere around that. And then you could get some, basically all of that back. So you only have this 2% in overall reduction in this total efficiency of the plant. So you would have this, and so all of this could be recovered as district heating, and then you would replace other units in the district heating system. So that you can do. That's about full scale. So the full scale unit is some 400 megawatt. It utilizes some 2.5 terawatt hours of wood chips, so this secondary biomass, which is branches and tops, is what we use, and some other discarded wood, bark, and sawdust, so secondary biomass. And so 400 megawatt, about 2.5 terawatt hours per year. And if we use CCS or not, it doesn't really change the amount of biomass we use. It's only that we have a prioritization in between products, which we also see in the power market in general, that we have a shift from just having a requirement for energy, because the amount of energy can be solved by solar and wind and maybe nuclear and other these non-CO2 emitting sources. That is, especially if we have a lot of wind and solar, then we need, or photovoltaics, then what we need is dispatchable production, so that we can actually, this production that we can turn on and off, and that we can still keep this capacity while having CO2 capture.
Are there alternative technologies, maybe for different kinds of plants, that are worth discussing?
Yes. So we could look at post-combustion. That's when, so in this case, we were looking at putting this actually after the flue gas pipe. So you could actually, above me is the big, see if I can turn the camera around again. So above me is this big pipe. This big pipe comes from the CHP. So here you have all the gases, and then we have a connection into that pipe where we draw out some of the flue gases into the test facility. So this is sort of after the whole plant, which basically means that you can retrofit existing units and with this capture technology. And you can also do it with a little bit less energy penalty. What you could do instead, so what you have is, you have the nitrous oxide, sorry, not nitrous oxide, the nitrogen gas, that's what you have, the N2, and then you have CO2, so that's basically the flue gases. And so you have the flue gases, and then you have basically what you do, so you take this CO2 out, and then you have the nitrous going up through the absorber, and then you let it back into the chimney and let it out with the rest of the air. And as I said, nitrogen is what the air is composed of mainly. So that is perfectly sort of the easy thing to do. If you want to reduce the energy penalty, I know that Vattenfall in Schwarzschild-Pumpe, they were looking at something called Oxy Fuel. So what you do then is that you put an oxygen factory in front of the power plant. So they run the power plant only on on pure oxygen. So then they never get the nitrous gas into the power plant, so that won't pass through the whole power plant and then back into the chimney. Then you would have a lower energy penalty in this regular power condensing or power station that you have abroad. So that's a good solution if you are abroad. Still this potassium carbonate is not for condensing units. The energy penalty would be too big. This is only good if you have a need for the recovered heat. So into district heating, or if you can use it for some industrial process in this more industrial CHP application. But for these options, if you have a regular power plant, then Oxy Fuel might be the best for them. I don't actually know that, and it will, I think, differ between different places. The other thing that has been looked a lot at is amine technologies, and amines have been used in the natural gas sector. The downside with amines is that amines are more complex. They could form cancerogenic substances as they react with different things in the flue gases, and they are also not as robust as this potassium carbonate. And the difference is that amines, instead of using pressure to have this reaction, they use a temperature difference. So the main thing in our process is this compressor, and that we compress the flue gases, and then we work between 7 bars and atmospheric pressure. That's sort of the fundamental of this. In an amine system, then you would instead use cool the flue gases and everything. Then in the absorber, you would have something cold, and then you would boil off the CO2 from the amine. And that's a totally different process. And from what we can see is that would be more expensive for our case. The cost per ton would go up, and then you would also be harder to work with because it's non-pressurized, more complex in many ways. You could also have actually higher capital. Even though you don't need a compressor, you still could have overall capital cost could go up, and the amines are proprietaries of different organizations that you also need to pay license fees or pay for someone actually manufacturing the amine, while potassium carbonate is something that you could find readily around. So.
Totally different question from Carl, who is wondering what's the velocity, like meters per second, of the gas in the absorber and dissolver?
I have no idea. I have some engineers that I could forward the questions. If you send me an email or this specific this text message at LinkedIn or something, I can look into forward that to some of my colleagues, because that is more specific than I know of, actually. So.
Excellent.
Sorry to disappoint about that. Yeah.
Something that you might have, I think you have touched on this, but question is, how should potential rebound effects be avoided? Like more CCS would, so to speak, leave more space for fossil fuel combustion.
Yeah, I think that's a tricky one. And I think everyone working with it don't really know the exact answers. I know that there are several projects looking into it. So we're part of this big Horizon project together with partners all over Europe, from Imperial, Oxford, Cambridge, some of the Postam, and in Finland a couple of universities and so on. And they are actually trying to sort of understand this sort of sustainable deployment of BECCS. I think what has to be is that policy for reducing CO2 emissions must continue to be put in place, and then it might be that corporations also need to seek bridge solutions in the meantime. But also I think, so if you look at some of the taxes that we have, so this here with including transport and storage, then we're talking about maybe 1,000 kronor per ton. That's sort of where everyone ends up, including the whole value chain per ton of CO2. That's higher than the EU ETS price. So if corporations would buy negative emissions to counter their present CO2 emissions, then that would be about 3 times more costly than just paying emission allowances. But that would sort of truly counter their emissions by putting the same amount of CO2 from the atmosphere into the ground. Long term, when we're talking about other sectors, so also to give a comparison, most measures that you do in traffic is from 2,000 kronor per ton and above. So if we're talking about these hybrid cars, then we're some 6,000 kronor per ton and so on. Trains even more. And then, of course, there are options that are a lot cheaper. So you have these productivity enhancing options in industry and such that have extremely low cost. So it's not the cheapest option, but it's cost effective in relation to many other things that we see in different sectors. So it's not extremely cheap, but it's not extremely cost either. But I think that having economic policy and other policy mechanisms go hand in hand that reduce CO2 and continue to reduce CO2 and see that you have the right, both economic and it could also be these technological standards and other things that see to that you continue to reduce emissions.
Excellent. I think we have about a handful more questions, unless you guys shoot even more. That would put an extra smile on our faces. What's the approximate size of the plant? You touched a bit on the size of the absorbers and desorbers, but
yes. So the landmark looking here at Värtaverket is so we have a full-scale design just being completed last week. So we had some heads up, of course, before about, and what we can see, you can build this full scale at about 1,400 square meters for the actual this catch unit, which is a little bit bigger, of course, than the container we're standing in right now. But it's still, you can fit it into Värtaverket, and then you need some storage, intermediate storage that you need just between ships coming in out of port, transporting CO2, and the liquefaction unit, which is sort of similar in size. So we're talking about maybe about some 3,000 square meters in total. That is sort of the amount you require. And then you could, of course, build it in different ways, different applications, different technologies will take different space. But some maybe 3,000 square meters is what you require. And I usually say this, if you can find place for such a unit in the middle of Östermalm, then you can build it anywhere in the world. So, yeah.
And for the salt that you showed earlier, is there any environmental impact of it?
No, it's a very safe salt. So it's not something that's toxic or anything. Then of course you need to handle everything responsibly either way, because you could get things in quantities. But no, and that's one of the upsides with potassium carbonate compared to amines, because amines could be both toxic and cancerogenic after you this maybe 10 to 20% that you need to replace every year. So that's also an upside with this particular technology.
Cool. And a wider question, how much biomass do we use per year to run this plant, and where does that biomass come from? Mainly Sweden or imported?
I think I answered that. So the biomass, it's so 2.5 terawatt hours. So in the energy sector, you measure everything in terawatt hours, because you always talk about energy. And of course, you could talk about tons or cubic meters or something. And I don't know in my head how to translate that. Then I will need to sit at my computer with a calculator. But 2.5 terawatt hours of biomass about. And the sourcing is mainly the Baltic region and FSC certified wood chips, or we do our own due diligence similar to FSC. So then we go to where they're going to make a cut, look, especially if it's abroad, looking that you have good environmental, good working conditions, good environmental conditions, that it's not competing with sort of these natural protected woods and so on and so on. So then we go in there in place if it's not FSC certified, but mostly it is FSC certified.
Well, and if you're a simple mind like me, you can answer the same quantity question with 3 wheelbarrows a second.
Okay.
I believe Fabian's answer is more informative. Another question about the salt. Can this salt have another life value? Like, it has a value after we produced it?
Maybe, I don't know. We haven't looked into that. So we're sort of trying to. We have done this first step, and for doing this whole testing this technology and sort of confirming that you can use it at a CHP, and a lot of this research into what you can do with the salt. Could you form different salts? Could you, by operating the plant in different ways, have different outcomes of salt and everything? All of this is sort of what we need to continue to develop and research. So it's a combination of business development that's ongoing and everything. So the simple answer, yeah, maybe. I don't know. It's worth looking into.
And a much bigger question, is there enough porous bedrock to handle large amounts of CO2? What's the capacity?
Yeah, I have to look up the exact numbers, but there is a very vast amount of porous bedrock, especially outside Norway, of course, and also outside England and some other places. So there are some places where there is a great potential for putting down CO2, and I think just in Norway they talked about that just the volume would correspond to 130 years of the total fossil CO2 emissions in Europe, just in Norway. But then of course you can't fill it to 100%. So, but that sort of gives in the known storage spaces outside Norway also. So something like that, and then you have other places. I think England has as much and so on. So there's plenty enough to if we cut fossil emissions and then we do the required amount of bio-CCS, then we could at least solving the climate change issue. It would be feasible in the law. Yeah, I think that's how I have understood it.
And the final question, which is good because it's nearing one. And another one popped up. So we have two more. And the first question was if it would be possible for you to share that process flow chart from flow diagram from the slides, or maybe could you share the presentation?
Yes, we could see to that. The question is how you will find it. So I think many found this. Some at KTH found this through email, and some others found it through LinkedIn. So I will post it in the same email and that I sent to KTH, and then I will post it in the LinkedIn thread somehow. So then you can find it.
Excellent. And then there was a question about what is the next step for Stockholm Exergi with this technology now that we have the design of the full-scale facility.
Yeah, so it's finding someone that wants to finance it. That's sort of a key thing. We know that so this governmental inquiry that was out, it was now on revision, and it was the suggestion was that the Swedish Energy Agency should be responsible for doing a reverse auctioning of negative emissions, starting with 1.8 megatons. And the reason why they put 1.8, that's because then they will get 3 to 5 projects going to sort of starting developing this sector, because it's larger amounts required later on. So if that would be one way, or there is someone on a commercial bilateral basis wanting to finance this, it's also something that we work on. But that's sort of the basics. Someone must require this and demand this economically, because otherwise it will not happen. And that's something we were working on. Then of course, now we have a design, then we need to go out, and so it's not, we haven't sort of negotiated contracts with all the ones that should build it and everything. So that would also require some time. You have all the environmental permits and so on. But what we say is that you could, if we get something in the governmental budget in autumn 2021, then we could have a full-scale facility up and running by somewhere end 2024 or early 2025. That is technically possible, but then we have a sort of quite squeezed production phase, but it's possible to do it. But then we sort of need to get done, because we're talking about big scale things. And just to sort of to understand how much 800,000 tons of negative emissions are. So before Corona, the domestic flights in Sweden, they emitted about 500 kilotons of CO2. So talking about 800,000 kilotons, so that's quite a lot more than all the air traffic inside Sweden that we have. So I think that gives a sort of good about the amount of negative emissions that just one plant would contribute with. Yes. Okay, thank you very much for attending this quick tour, and I hope you enjoyed it.